Hello everyone and welcome to this first lecture on geodynamics and visualization. The aim of this little presentation is to give you a little bit of motivation based on geodynamics to go through some practical programming exercise that will give you some knowledge about visualization of data and models in geophysics. If you recall the lecture of last week, you should remember that the Earth has a spherical shape and consists in several shells. It contains the solid inner core, the liquid outer core, the lower mantle, the upper mantle, and the last shell here is called the lithosphere. The lithosphere, it contains a rigid part of the mantle and the crust, which is very thin. And if you remember, we have the continental crust as well as oceanic crust on the Earth. The total radius is 6,400 kilometers. And you should also know that the age of the oceanic lithosphere varies in space. So here is a map of the age of the oceanic lithosphere. And what you can notice is that you have red color in the middle of the oceans. This means that the age is very young. So the material which is here has just been produced. It's been formed very recently. And when you go away from the mid-ocean ridge axis, then the color turns to bluish until purple colors. So it means it gets older. So you do have a trend, and there's a space-age relationship in the oceans. This is indicating a dynamic aspect of plate tectonics, basically that material is being created in the middle of the ocean and drifts away towards the continental sides. So the youngest oceanic material is found in the middle of the oceans, and the oldest one is hardly older than 180 million years on Earth. In contrast, if you look at the age of continental materials, now you have a different color maps, but these color maps apply to the different continents. Then you see a little bit of purple, a lot of yellow, orange, and a lot of blue. So what does it mean? Here you can see that there's a little bit of continental crust, which is actually young. So most of the continental crust is rather old. Most of it is more than 100 million years old. And locally, the continental crust can be very old. So what does it mean very old? It means you can go back to the Archean age. And this is what you find in the cratons here. You don't have a very nice trend between the age and the spatial position. So it's a different pattern than in the oceans. So you have contrasting history of oceans and continents on Earth, and you also know that plates are moving. This is now a nice visualization of velocity vectors and plate boundaries. So you see the plate boundaries in green here and the velocity indicating the direction and the magnitude of the surface motion of plates. This can be, for example, probed by GPS analysis. The plates move relatively to each other, and the maximum velocity would be the Pacific plate, which has a relative velocity of 10 centimeters per year. So that's very fast. Over the course of the geological history, one may try to reconstruct the geodynamic history of the Earth. So this is a little movie showing you the breakup of a supercontinent, Pangaea, and this video starts at 200 million years ago. On this you see velocity vectors. So that's the result of a model here. We cannot measure with GPS velocity the velocity 200 million years ago, but we can try to model it back in the past. I run the model forward and you will see a lot of events happening with the opening of the North Atlantic here, for example. Progressively, the rifting of India away from Africa. Soon this entire ocean will open and the South Atlantic oceans open last. Now you will notice the position of India. It's now accelerating and it's going to enter in collision with Eurasia in order to form the biggest mountain belt on Earth today. So that's a very nice movie of the last 200 million years on Earth. So we see a lot of surface processes and some of them are very impressive and they should tell us something about what's happening deep in the Earth. And you see also very nice visualizations here. So this is taken from Google Earth. It's a picture of the eastern side of Australia. So you see the Australian plate on that side, the Pacific plate on that side. Here is a very darkish blue color indicating a very deep trench of a subduction zone here. And on that side here, you see an explosion, and that's the Hunga Tonga 2022 eruption that took place there in close relationship with this subduction. So it's subduction volcanism. So we may ask, we've seen a lot of pictures now of surface observation, but what about the depth? And here, since we're talking about a subduction zone and the processes occurring at subduction zone, we may ask, how do we know that subduction zones exist? And there's, of course, a very important role which is played by geophysics. And this comes back to early seismological studies. What you can do with geophysical method, you can probe the current day status in the subsurface. And it's an indirect probing because we try to measure some physical properties below the surface of the Earth. And one thing that can be measured is, for example, the focal mechanisms or the hypocenters of earthquakes. And you see here two sections taken in the region of Tonga. And what is being plotted on this section is the position of the hypocenter in a depth x coordinate. So now we get an idea about the structure at depth. You see a lot of earthquakes happening in two regions here, mostly two clusters, and this is extending down to 700 kilometers. So we see hypocenters at depth and the occurrence of very deep seismicity down to 700 kilometers. This already shows you a pattern. Another type of study that can be done today with seismological data is seismic tomography. So seismic tomography aims at reconstructing the distribution of seismic velocity at depth. Now look at the scale. You again have a x depth color map, and this color map goes from red to blue, and it indicates you a variation of the velocity of P waves with regard to a reference model from -6 to 6% deviation. And with this method, you can also see or relate the variation of velocity to some pattern here. So you see this structure which is dipping down into the earth and on which overlays the little circles here, which are the hypocenters of the earthquake we saw on the picture before. So thanks to both of these methods, we can reconstruct a structure which would be the structure of a subduction zone. When we cannot observe or when we want to understand the processes over a long time scale, we may want to use modeling. And to model the Earth interior, it's very common to use thermomechanical modeling. And I will show you now a nice movie of a convection model equipped with plates at the surface. So the mantle, it's an upper mantle scale model with thermal convection taking place and plates which are moving and breaking apart from each other in 2 dimensions. So that's the type of computational fluid dynamics simulation that are being run to understand the internal dynamics and its effect on surface, how those plate breaks and reconstruct supercontinents. So in all of the slides that I've shown you until now, I've shown you very nice pictures and want to understand that the visualization of data is very important in geophysics and geodynamics. It's central. So here's an example taken from a book that shows you one model, and this is one snapshot of a model that shows you a subduction zone and a lot of processes like a collision taking place between these 2 plates here, a slab which is breaking up or detaching from the subduction zone here. You can zoom on it, you can see the temperature structure, you can see the internal structure of a collision zone. You see many things. You can analyze the temperature field, you can analyze the viscosity field, or measure the strain in these structures. You can do a lot of things with the model, but if you don't use visualization, manipulating and extracting anything from the data of a computer simulation or a huge data set looks a bit like this. So it's absolutely unusable. It's a lot of data just written to disk or stored in the RAM, and it's difficult to interpret anything by looking at this big table here. So yes, visualization is important. It's actually a golden rule number 6 in the book of Geria 2019, which I recommend reading. So it's important to make first steps with visualization. So this week we will start our exercises of visualization. So the first step, we get Julia and VS Code running, and we will get familiar with basic data generation and visualization. So there will be 2 notebooks which we will use for our exercises. One will consist in training in array programming and basic 1D and 2D visualization. The second notebook will be a bit more practical. We will plot the 2D structure of the Earth using the tools we learned in the first notebook. So, training in array programming, you will quickly realize that you need visualization, even if we only look at a 1D exercise here. So that's one of the exercises you will learn, you will do, and the aim will be to learn how to create a simple plot, simple graphics, but also using scatter plots and plot several lines on the same diagram. That's one important thing to do. The second part of the exercise, you learn how to generate a 2D Gaussian field and how to visualize it either with a contour map, a contour F here, or simply a heat map. In the second notebook, we will construct the 2D structure of the Earth, and we will use 2 different approaches. The first approach here will be to simply draw circles. So we will use the equation of a circle and plot different circles for each of the layers representing the main shells of the Earth. And in the second part of the exercise, we use a totally different approach. instead of drawing lines, we will create a pixel map, and we will attribute to each of the pixels a color based on the position relative to the center of the Earth. This will create a pixel map of the structure of the Earth. So, thanks a lot for your attention, and see you at the exercise.